Hi, everyone, and welcome to this episode of Crowded Beaker Solves. Today, we're going to be looking at a couple of Lewis structures that involve something called resonance. And if you've never heard of resonance before, just wait till you see these Lewis structures and you'll see why we need to introduce this concept of resonance. So let's get started. My prompt here says selenium dioxide, and that's the molecule we're going to draw. I'm going to be, again, modeling the steps for drawing a Lewis structure. And if you want to review those steps, you can go back to the first video where I talk about them more in detail. But selenium dioxide, the first step you have to do is to add up the valence electrons. Selenium and oxygen are both in the same column of the periodic table, column 6, or 16 if you're doing the 1 to 18 numbering. But it has 6, it's in the 6th tall column. And so it has 6 valence electrons. So does oxygen, for a total of 18 electrons. That's what we have. That's our pool of electrons to do whatever we need to do it to make this molecule happy. And so we're going to go ahead and put the selenium in the middle and put a couple of oxygens on it with a single bond to start. That's the second step. Draw the skeleton structure. Then we're going to add some dots around the oxygen so that they have an octet of electrons. And I've used up 16 electrons now. Any remaining electrons, this is step 4, go on the central atom, even if doing so results in more than an octet. And I get this situation where I've used up all 18 electrons. And at this point, we have to sort of sit back and say to ourselves, okay, is that central atom happy? Is it satisfied? Does it have an octet, or at least an octet? And in this case, no, it's not. It's got 2, 4, 6 electrons, but not 8. And here, when we have a shortage of electrons, we've run out, but the central atom needs more, we need to do a double bond. And so I'll just go ahead and just pick this one. I'm just going to cross that off. You got to pretend that's not there anymore. This is going to go into the middle, and I'll make a double bond so that those electrons can do double duty for both the oxygen and the selenium. And now I've created a molecule that satisfies the octet rule, and I'm pretty satisfied with it myself. But you might be thinking to yourself, well, why did you do it over there when you could have actually done it over here? And that is true. That's a good observation. In fact, I can write a second one with the double bond on the left side. Oh, and the lone pair. And that is also an equivalent Lewis structure. It's doing the same thing. It's like we're looking at it from the other side now, and it's on the left instead of the right instead of the left. And so those are both satisfied. And in fact, both of those are what we would call resonance structures of each other. Resonance structures. And resonance structures happen when you have a double bond that needs to be added, but there's more than one possible place that it could be. Or maybe you have doubles and triples that can be in different places and still satisfy the octet rule. And so it's actually more appropriate for us to draw both of them because they both are valid. And in fact, the selenium dioxide actually probably exists in both of them almost simultaneously. The electrons from one, they're mobile. They can move wherever they want to go. And so there's no reason why these can't jump back onto this oxygen and be replaced by these. And in fact, the selenium dioxide molecule will very likely be just swapping back and forth between which side the double bond is on thousands and thousands of times every second, and basically existing as sort of an average of both of those. It's oscillating, it's resonating, it's shifting back and forth. And so we call these resonance structures of each other. And so if you ever get a chance to get into a question where it says draw all the resonance forms of a molecule, you can plan on drawing it at least 2 times and maybe more than that. So just draw both or all of them, and then you'll be more appropriate than just adding or drawing one of them. Okay, so it's your turn now. We're going to draw the Lewis structure and resonance forms for sulfur trioxide. So there's our prompt. Take a moment, pause the video if you'd like, try to draw these molecules, and then come back in a second and we'll check the answers. Okay, if you were able to do it, then congratulations on finding out that there are 3 resonance forms of sulfur trioxide, because with 24 electrons scattered around 4 atoms, you need a double bond somewhere, and there are 3 identical places that you can put it in. So you should actually have the 3 SO2 or SO3 Lewis structures as the resonance forms of that. All right, so there you have it. Simple molecules that exhibit resonance. And if you have any questions or request of anything you'd like me to draw, stick it in the comments or message me. And in the meantime, have a great day and happy drawing.